Anyways, next we're going to talk about open addressing. So we've previously talked about separate chaining. So I'm going to give you a high-level discussion of open addressing. I'll have more careful details in the notes. So the first thing I want to point out is that there is a drawback for separate chaining, which that was a previous collision resolution approach that we talked about. So if space is expensive, separate chaining may not be ideal. So you have a very limited amount of memory you can use. It may not be ideal because every time you're going to have to use that additional memory, you may also have to deallocate it a lot of the time if you're deleting a lot of things too, right? Just keep that in mind. If you have a fixed amount of space you have for your table, we want an alternative to this closed addressing approach where you actually use every one of the addresses, but they map onto the exact spots. So we're going to relax the way we can address the table using an idea called open addressing. So I'm going to move my friends from the theater here so that they can kind of relax a little bit more. So here's the idea. So first, one thing I do need to make the remark on is we're going to use the entirety of our table. So we're not going to be making we're not going to allocate more memory for our table to make this work. So I must stress, we need to have a consistent way. We're going to presume that we're going to assume that n is the number of records or elements is less than m, meaning that so the load factor alpha, which is the ratio of the number of records and elements over the number of table slots, is less than 1. So also a couple other things. First, we're going to use every bit of our table. So we're not going to be mapping into like new memory locations or anything like that to make this work. We're going to use the table as given. The other issue is that I would like to have it. I would like to know what the initial state of this table looks like. So I'm going to assume that the table just has null pointers or null references, depending on which programming language you're talking about, in every one of the slots of the table initially. So here's the main idea here. So I'll elaborate on this in a moment. So whenever we're doing insertions, removals, or we're searching, we check the position of h of k, but we check that content's in there. So we check at the table in that given spot. If null is there, I say position at. So check position, we check this right here. We check that table slot. If null is there, then we can insert. Another interesting question. If null is in fact there, does it exist in the dictionary or map? No, it just doesn't. So the hash table, we know it isn't there because nothing's there. It's hence why we can safely insert. I'll say insert safely. I'll put in parentheses safely. So I must stress that this right here is the position in the table. I'm just wanting to examine what's there. Okay, so next, what if there already is a record there, a key value pair? So otherwise, a record is there. So we need to find a different spot, in the table, to put our new record, right? So there's two issues at hand. So first, if we already have something in that spot, the hash function will get us to that spot. But there's another issue. What if ever I want to access this record in the future? Can it be that this way I access it, can it be like something that changes on a whim? Maybe, maybe not, but either way, it's probably not a wise idea, especially in this setting. So I can use the hash function to tell me where it should be, but then I need to know how to get to this other spot or other slot in the table. So in open addressing, we're going to use the idea of what is called a probing sequence. And that's going to be the heart of this. A probing sequence. A probing sequence tells us where the next position the check is. And repeat. So you can examine there, see if it's null. If, say, if we're doing an insertion, then you can safely insert it there. If not, then you apply the next instruction from the probing sequence. This probing sequence tells us a sequence of positions, and the sequence is defined by performing some simple operation. I'm going to give you two examples of probing sequences here. But the idea is for collision resolution, is as follows. So it says probe. So probe to find the next available slot of T using a probing sequence. So I'll define what I mean by this in a moment using a probing sequence. Okay. So you might ask, Dan, what do you mean by a probing sequence? So come back here, camera, come back here. So let me tell you what's kind of like all about of this, okay? So in separate chain, the way it worked when I took my friends to the theater, the way this worked was it was possible that if I ever got the same position that they all wanted, they would all get stacked on top of each other. So let me give you an example of what I mean by a probing sequence. So suppose my hefty friend here, very lovely person, say they like this spot. And say my giraffe friend comes along again and says, I really like that spot. Well, surely I can't put the two in the same spot because I'm not going to allocate more memory. I'm going to use the table as is. So one example I can do is I can tell my friend, my lovely friend the giraffe, to go to the next spot. You go to the next spot over. So and this is something that you might do at a movie theater. Say, I like that spot, maybe I'll go right beside them. But the thing is, I'm going to tell them to always go to my right, but if I start running out of room on this side, then I'm going to let them come back to the first one. So say, for example, my little sleepy friend here wants to go in this spot. Well, we'll check this spot. Well, this one's already occupied, so we'll check the next spot that we established. So we'd go to our left here, and then we would check, hey, is this available? No, my lovely giraffe friend is here. So I'm going to then go to the next spot that's available. So I'll go and put my friend here because my friend can fit right there. There's nobody there, right? Well, naturally, what we're going to do is we're going to just use some pretty basic modulo arithmetic to do something like this, where we're going to incrementally or if you think of it from the top-down perspective, we would get them to the next spot below, and below, and below, and below. We'll go to each successive spot, examining if they can go there. If we don't find any room anywhere, that means the table's full, right? So, let's talk about that. So, the idea I just described to you is what we call linear probing. So let's talk about that. So it's the first of the two probing sequences I was going to define for you. So on a collision, check the next successive position modulo m. We talked about that before, until a spot to put the record, put or get or remove respectively, is found. So here's what the probing sequence looks like. So first I check h of k. If there is, so if, for example, if I'm doing insertions, I would check this spot. If it's null, then I would stop here. If I don't, then I examine this following next position. I would check h of k plus 1 mod m. If this spot is not occupied, then I would insert right here. If it isn't, then I'm going to go to the next spot over. So next I would check h of k plus 2 mod m. Again, same idea. And then you would keep doing this. You would have h of k plus 3 mod m, and so on. I must stress that this probing sequence, this scheme, does not require that capital M be a prime number, but some of these open addressing techniques actually do rely on the necessity for the table size to be prime. That's one I'm going to talk about in a moment. So here's the way I like to think about this, is that I like to think of it like I'm a bunny rabbit. So imagine if I was a bunny rabbit and I'm trying to find my hole where I have my naps. So I would first start off where I think the hole is, but if the hole isn't there, then I have to hop to the next spot I would check. To help me remember where it is, I need to make sure I follow the probing sequence to tell me where to go to find my hole. So in my case, if say I get to h of k, but there's no hole here, I would hop to the next position. I would check if my hole's there. It's not there, so I'm going to go to the next position. I hop to the next spot, and I would keep doing this until I hit a spot where there is something there, a hole that I can hop in. This is just like null. So you can imagine like a bunny rabbit trying to find their hole to have a nap. Isn't that nice? So that's the idea behind linear probing. So I thought it'd be a good idea I do an example with you. I'll have pseudocode for inserting and searching in the notes. But one thing I must stress is that you're going to need an additional check than just simply examining each one. You have to make sure that there's a cap on that you don't examine over and over again all the positions, right? Because keep in mind, you can keep doing this forever, right? Because it's mod m. So you need a cap when you're doing this type of search process, where you'll be inserting, removing, or searching. So you need to check until you've examined every slot in the table. If you've examined every slot, then so if you're, for example, doing a search, then you know it failed, right? You couldn't find anything. If you have no more slots, then you can't insert anymore. If you're trying to do a removal, your removal failed because you failed to find it. So that's one small check you're going to need to include. So I recommend you have a counter variable keeping track of this. But otherwise, it follows a very similar setup to the search algorithm I gave you for separate chaining, except instead here, you're going to apply this probing sequence where you just take our position, you increment it up by 1, and then you apply mod m. So you just go to the next position. You're going to see this in our example here. And you're going to find out very quickly that the time complexities that we obtained before for separate chaining are going to be just as true here. For very similar reasons, just the difference, of course, is that how many average number of collisions you're going to get might differ. So I thought we would do an example. So let me head over here. So I'm going to talk about how you might do insertions, and then how we do insertions, how we search, and of course I'll make some remarks about removals, and then we'll see there might be an issue with our linear probing. I must stress that linear probing is very cheap to do. It's also fairly fast to do. So notice all I have to do to find the next spot is just increment a counter variable. So it's very simple. It's just like the other one I gave you, except now you're mapping inside. The mapping is within the table. It's not following a linked list. It's just accessing spots in the table. So let's do an example here. Suppose that I have m is 9. So this is my table T. Say I have 9 slots, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for the sake of brevity, if a slot has nothing in it, just presume a null pointer or null reference is there. So this is going to be my hash function. H of k, or h given k, is k mod 9. And we're going to have the following records we're going to place in here. We're going to have 18 v1, 16 v2. We're going to have 8 v3, 44 v4, 3 v5, 1 v6, 19 v7. So these are all the records I'm going to put into this hash table. So let's start off with 18. So if you put this in, well, let's think about it. 18 mod 9, well, 18 is 9 times 2, right? So they cleanly divides, there's no integer remainder, so you know 18 is going right here. For the sake of brevity, I'm just going to write down the key as opposed to the value with it. So far we got 18 in. Next, let's go with 16. So 16, well, 16 is 2 less than 18. So it means that it's going to be 2 slots away from 18, but they're 2 less than 18. So that means it's going to be 1, 2, 2 less. You gotta remember, think of it like a wraparound. So whenever it gets bigger, it goes back like this. If it gets smaller, it goes back like this. So 16 goes right there. Okay, how about 8? Well, 8 mod 9 is 8. So far, nothing too interesting. There's no collisions or anything yet. 44. Okay, that's 1 less than 45, right? Because 9 times 5 is 45, right? So that's 1 less. What does that mean? It means it will go right here, right? Because 44 mod 9 is 8. So remember, 44 9 is 8. It's because it's 1 less than 45, which cleanly divides 9. So now I have a collision. There's a collision that happens. So there's a collision. So I have to apply the probing sequence now. Remember, think of me as the big bunny. I'm right here. Where am I going to go? I need to go to the next spot, mod m. So I would take 8 plus 1 mod 9. That's 9 mod 9, which brings me up here. So I make one hop. I make one hop to position 0. There's something here though. So what does that mean? The bunny needs to hop to the next spot over. So it's h of k plus 2 mod m. So before when I add 1, I get 0. When I add 1 again, I get 1. So bunny hops, finds a hole. We can put 44 here. So next, let's do 3. 3 is a piece of cake. Because 3 mod 9 is just 3. 1, well, same idea. 1 mod 9 is 1, but this is occupied, so I'm going to have to hop. The bunny hops, puts me right here. Do you see when the hops occur? One very important thing I really want you to notice, like I was saying earlier, I need some way to know and help the bunny get to the hole, right? So say, for example, when we did the insertion of 44, I started here, then I hopped up to 8, this position here, then I hopped right there, and I found a spot, right? Notice this is a chain of hops that I'm trying to preserve so that I can always ensure I get to this. So please keep this in the back of your mind, or keep it as a feather in the back of your cap. It's rather important for this. So next, we've got 19. So 19. Well, 18 mod 9 is 0. So 19 mod 9 has to be 1. That's 1 higher. So I get to be right here. Well, that's not available, so I go to the next one. So the bunny hops, then the bunny hops again, and then the bunny hops again. So that brings me at position 4. And now we've done all of our insertions. Piece of cake, right? Piece of cake. So now the real natural question is, okay, so if ever I want to get, say if I want to get 44, I use 44 mod 9, that gives me 8. So position 8. I know 8's right there, but it's the position, right? 8 plus 1, 8 plus 2. Remember, this is all mod m, right? So notice that gets me the 44. I preserve the hop, so the bunny can hop to the appropriate spot. So if I want to do insertions, if I do a removal, actually, before I get to removals, as a remark, notice that if there was, in fact, a duplicate key that I was going to attempt to put in here, it would have to fall along this probing sequence, right? Because it would have to exist along the chain of hops, right? So be aware that you can't just simply just be like, yeah, look, I just hop, I find the spot. But remember, when you're doing insertions, you have to check if it's the same key, right? If it's the same key, then you have a duplicate and you cannot put it in. It violates the properties of a map or dictionary. How about removals? How about a removal? Let's think about this. Say, for example, we had 19. If we have 19, if I wanted to get rid of, say previously I said, I'm going to get rid of 3 here. Can I do that? Can I just get rid of 3 right there and just leave it at that? Make it null? Does that make sense? Well, let's think about it from the perspective of the bunny again. Okay, 44. Okay, I check 19 mod 9. That is 1, right? So it puts me right here. The bunny hops. The bunny hops. There's a hole here. There's a hole here. If I'm trying to search and I hit null, that means that the search failed, right? Meaning it doesn't exist. But the thing is, it most certainly exists. It's in the next slot. But that's a problem, right? We need something here to help us make sure that the bunny doesn't fall into the hole in a place that's not intended, right? So that brings me to talking about what is called lazy deletion. So one way you can resolve this, so there's 2 ways you can resolve this issue. The first way is you could just simply rehash the entire table every time you do a deletion, but this is very expensive, as I explained previously, if your table's rather large. If it's small, not so much, but if you're doing this many times, it can be. Another idea, this is one that's used quite often with tables, and sometimes used in systems. For example, it's the idea of lazy deletion. So whenever I do a deletion, instead of it just being saying, hey, look, instead of it being where I just get rid of this and that's null, I'm just going to mark it as something to be deleted. But it must be stressed that this label that I have, this marker, is not equal to null. Nor is this is also not equal to the keys, just to be very clear. So whenever you're doing your search, it's not actually a hole. It's actually that we help the bunny by putting maybe a basket on top to make sure the bunny can't fall in the hole. So that the bunny can continue hopping as if it wasn't actually the key that matched. So this idea is called lazy deletion, and sometimes these markers are called tombstones. Like that would be called a tombstone. So some people call this introducing a tombstone. The one issue that you're going to run into very quickly, however, if you have many of these tombstones, what happens is that it may degrade the performance of this. If you have many more deletes than there are actual keys in this table, that might degrade quite a bit. So there's a couple quick ways you could resolve this, for example, is one, you could check for the duplicates first. If there is no duplicate, so you check for duplicates first. I must stress that the algorithm I have in my notes doesn't do this. But if you check for duplicates first for an insertion, so if you're doing a put operation, if you do this first, then what you could do is if you encounter a delete like this, you can actually put your new record right into where that is, replacing it. And it helps get rid of some of these tombstones, but it's not going to really solve everything. The other way you can do this is just simply rehashing the table. So just keep an eye on the load factor, for example. That might be one way to help you try to figure out if you need to rehash the table. So an important remark I want to make is the time complexities here. So do you see very quickly that if I fill up this table, many entries, it's possible to have a probing sequence. The bunnies, so that they hop, all of them go through the entire table. Hello. No, welcome on in. So we're just about gone through all. You could have it where all of these table slots get hopped over, so the bunny hops over all of the entries. So all of these slots get used. That's not good, right? So in the worst case for our get, put, and remove, so insertions, searching, and removals, regardless of this tombstone business, which you might think of even as just slots where nothing equals any one of the keys. For all of these in the worst case, you have to potentially go over the entire, all the records, right? Especially if you have a really bad hash function, just like we talked about for separate chaining. Say, for example, all of them are multiples of 7. Do you see how, actually, no, in this case, in this example, make them all multiples of 9. Say if you had 9, 18, 27, 36, 45. If you have all of these, if you have all of them, notice that you would have it where the bunny every single time always goes, it has to make one extra hop every single time. Isn't that amazing? So that's actually how you can create worst case instances here. So the worst case here is big ol' event, meaning it takes linear time, linear in the number of records. But as per the rationale I gave a little earlier on for separate chaining, because the load factor is less than 1, you can actually bring, in the average case, it actually behaves such that it takes constant time. But remember, this is under the presumption of our uniformity assumption, the one that said that all of our keys are uniformly spread. Spread like, butter on a nice smooth bagel. It's something rather important. So this is, remember, this is with a good hash function. Yeah, good hash. It's a good hash. So naturally, so one major issue we're going to run into very quickly is what is really the thing we have to think about with linear probing? Well, do you notice that in my worst case example that I just brought up, how if I have multiples, or in fact we even encountered something like this in this case right here. So do you notice that if I was trying to search for 19, so I would show and go 19 mod 9. That would give me 1. And I would have to go through all these hops like the hoppy bunny rabbit. So I'd have to hop, 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 go checking 44, 1, delete, then it gets to the 19, right? So if I do this, this actually forms something called a cluster. And in fact, it's very easy to build these, what they're called clusters in linear probing. And that's a drawback that this has. It makes it so it degenerates if the load factor gets rather big. Now anytime, now have yourself a beautiful day. No, wonderful. So we have the clusters. These clusters can form and they can get really long. As I said, the naturally largest cluster is when all of the clusters become one giant supercluster. So naturally, we would like to have some way to alleviate this idea of a cluster. So it's very easy for these clusters to form when you have subsequent keys appearing, like one after the other, or they all hash the same position, meaning we get a long chain of collisions that happen. So just like my example with 19, if I were to, for example, to put, well, we have 1. Say, for example, we had, let's go 28. Say if you had 28 here. Say if I went 28, I would have to check this one, this one, this one, this one, and I would put 28 right here. It would extend the cluster by 1. So in separate chaining, we encountered this by just making the linked list longer. In linear probing, they form these things called clusters. So what I would like to do, one natural way to try to resolve this issue is by trying to spread out the indexing of the positions for our probing sequence. So instead of having the bunny hop from one position to the other like this, instead, we want to give the bunny rocket-powered boots. Yeah, try to imagine like a cute little bunny going at rocket speed, just zoom. I would like some way that this bunny can hop pretty far along on my table. So instead of it being where I go hop, 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 instead we want the bunny to have the ability to really make those excess jumps so we can try to avoid clustering. Now, it does not ultimately resolve clustering, but it most certainly will alleviate it. So instead of it being one hop like this, I would like to make it so it hops instead more like this, where it hops quite a bit of distance. So that's going to be one other issue that we want to resolve here. So linear probing, fast, efficient, and it also has this property that it's fairly easy to implement too. Like, remember, this is all just within the table itself. But the probing sequence we have has issues. So it brings me to the next probing sequence. And I lovely set it up like this so we can save ourselves a little bit of time here. So let's talk about double hashing. So again, like I said, if you're looking for the pseudocode for these things, I have the notes. They're available on Patreon, on patreon.com/PageWizard. Sorry, I'm getting really excited here. Yeah, you can check out PageWizardGames.com for anything when it comes to this. So I got double hashing. So here's the so remember, the idea before we would hop 1, 2, 3, 4 potential hops, but they're always by 1, right? What I would like to do is I would have it so that it's able to scale and make the hops larger. And I want it to also depend on the key itself. So I want it to be able to affect how big the hops are. So they aren't all going to be uniform in their size. It depends actually on the key, what it outputs to the hash function. So what we're going to do is we're going to introduce a secondary hash function. So some people call H the primary hash function, and this other one's going to be called the secondary hash function. Sorry, I can't seem to write today. Introduce a secondary hash function. We're going to call this H prime, where its input is going to be a key. But I want to have, so we're going to have it so that it allows us to have differing hop sizes. So this is what its purpose is going to be. So we want to make it so that the hop sizes differ. Now, this is what the secondary hash function is going to be used for. So the idea is we're trying to make it so it isn't going to be where they're all just going to clump up again. Now, they might clump up with a specialized, tailored scenario, but most certainly it will not give you the same situation. This is going to look at more like a generalization of linear probing. So anyways, let's see here. So as that being said, it's supposed to give us the size of the hop. This is one important technical remark I need to make. I, in fact, have two of them. The first one is that the hop sizes can never be 0. Otherwise, our bunny's just going to sit there just kind of hopping over and over and over and over again in the one spot. And that's not going to work out well for us, right? So we need to make sure that h prime of k is never 0. Note. So the first thing is h prime of k can never output 0. You're not allowed to have it so it pops out 0. Otherwise, it will not allow our bunny to hop anywhere. That's a bit of a problem. Now, there's several other kinds of secondary hash functions you can use. I'll give you one that's fairly common for double hashing. This one will set up things nicely for us. So I'll say an effective. An effective h prime, where our given k is as follows: q minus k mod q. And now I must stress that q, which is going to be less than m, is prime. So q is a prime number. So if you've never heard of prime number before, it's a number where the number of divisors it has is exactly 2. 1 and the number itself. Sorry, I'm getting very excited here. I just got to calm down. So this is a very common one to use as a secondary hash function. But please note that in this case, I have one other very important thing I need to tell you about double hashing. Is that for this h prime, m, the table size, must be prime. That is key for this to work. I'll show you an example of where this all breaks down pretty soon. So remember, linear probing, you only make a hop size of 1. In this double hashing, the hop sizes will now differ depending on h prime. So now I want to give you the probing sequence, okay? So let's see the probing sequence. So to make this a little easier for us to see, and I must stress that the time complexities will not differ from aspect in terms of big O for double hashing, because all I'm doing is just changing the probing sequence. You can still have the nasty situations happen as exactly I described. Just the thing is now we're trying to reduce the clustering, which ultimately will try to reduce the average numbers of collisions. But remember, at the end of the day, if you have a fixed size for some of these parameters, you're going to be okay. Remember, the load factor is less than 1 always here. Or it's at most 1, to be a bit more precise, if you want to allow the table to be completely filled. So here's the probing sequence for double hashing. So here it is. You try out h of k first. So you try that. If that is going to get you what you need, for example, if we're doing a search, if h of k is what you're looking for at that spot, then you're done. If it isn't there, then you're going to check out h of k plus h prime of k mod capital M. So notice that instead of it being a 1 here, now it's h prime of k. And now each time I take a step, instead of it being just one step, it's going to be multiples of h prime of k. So plus 2 times h prime of k mod M. And if this fails, then I try h of k plus 3 times h prime of k mod m. And so on until you've checked the entire table. Or you get my point. So all I've done, everything I've just described to you about linear probing is just going to be the exact same here, except you're just going to replace the probing sequence with this one. That's it. That's all double hashing is. So instead of this being 1, 2, 3, it's going to be 1 times h prime of k, 2 times h prime of k, 3 times h prime of k. So remember, we're giving the bunny rocket-powered boots. So instead of it being 1 hop at a time, it's going to be that the bunny might be able to have hop sizes of 2 or 3 or 4 or potentially more. So instead the bunny might be able to do this, like 1 hop. And I worry if I jump too far that way, I'm going to totally slide nastily. So I'm going to... It's supposed to be the same size, by the way, there. But my point stands, hopefully, is that we're giving... So if we had our little bunny... Here's my cute little bunny here. Here's my cute little bunny. See, there's the cute bunny. Got little cute legs. It's got one of those cute little legs. There's his little floofy tail there. Look at this cute bunny. The bunny makes hop sizes of 1. Originally in linear probing. Keep in mind that you can craft double hashing so it gets you linear probing back. I'll let you think about that. Instead, we're going to give our bunny rocket-powered boots that have rockets. So the bunny now can hop. Instead of it just being by 1, it's h prime of k. And now the bunny is extra edgy. Now we're going to give the bunny some cool shades here. Oh yeah, there we go. We'll get some shoulder pads on there. There we go. That's a mean bunny. So this will help us try to alleviate these clusters, okay? And that's all we do to change this process. So I'll have an example. Actually, let me do an example here with you. So let's do as a different table. Just because, remember, 9 is not a prime number because, say, its divisors, for example, would include 1, 3, and itself, 9. So it's not a prime number. So let's do an example, just so we can see how this plays out. And I'm going to show you why it's so important that the table size is always a prime number. So watch this. So let's do an example. We're going to have 7 slots. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 6. We have our table T. Its table size is 7. And we're going to have it, so our hash function is h of h given k is going to be k mod 7. And a secondary hash function is going to be h prime given k is going to be 5 minus k mod 5. So notice that I picked 5 because it's less than the table size and it's a prime number. 5 is indeed a prime number. If you're not sure about that, just check it yourself. Try numbers 1 through 4 and see if any one of them other than 1 divides 5. So anyways, we're going to be inserting in the following records. So we're going to put in a 1, a 8, a 3, and a 29. So I'm not going to worry so much about the values. I'm just going to look at the keys. So to work with each one of these, I'm going to first apply the hash function. So I'll apply h of 1. That gives me, let's see, 1 mod 7. That's just 1. So 1 goes right there into the first spot. There's no collision. 8. Okay. 8 mod 7. Well, that seems like it would be, well, because 7 mod 7 is 0, right? So 8 mod 7 is 1. That means we have a collision right here. So it's a collision that happens. So we need to now consider a probing sequence. So we check this one. That's a dud. It's not going to work. So now we're going to try h of k plus h prime of k. So let's figure out what h prime of 8 is. So let's see what h prime of 8 is. Well, it's 5 minus 8 mod 5. Sorry, I'm cutting it a little off here. So we have 8 mod 5. Well, think about this. 5 mod 5 is 0. This is 3 higher, so it's 3 mod 5. So we have 5 minus 3, which is equal to 2. So the bunny is going to make hop sizes of 2 for key 8. So we're going to start here because we got a collision here. We're going to hop by 2 over here, and we see we could put the 8 right there. Now note, if there was something here occupying this, I would hop by another 2, and then another 2, because these are multiples of 2, our hop size. Remember, our bunny now can hop by sizes of 2 for 8. You're going to see that now it depends actually on the key that we give for the secondary hash function. So sometimes its hop sizes will be 1, sometimes it'll be 2, sometimes it might be 5. It's hard. You have to check. Okay, now let's try 3. Well, h of 3, that's just a piece of cake. That's just 3. Well, oopsie daisy. That's going to be a problem. We have a collision, because we already have 8 in that slot. So let's figure out what h prime of 3 is. So we have 5 minus 3 mod 5, right? Which this is still 3, right? This is 3. But 5 minus 3 is 2. So it has the same hop size, right? So it's still 2, just like we had before. But this is just a coincidence, okay? Remember, this is just a coincidence. So now I have my position 3. I make a hop size of 2. And that brings me down here. So I go, there we go. 3 goes right there. Piece of cake, right? So remember, whenever there is something in the spot, we peel to the probing sequence. So I suggest when you're doing this, figure out what h of k is. Then if you get a collision, figure out what h prime of k is. Then you're going to jump by that hop size. How about 29? Well, let's see. 28 mod 7 would be 0 because that's 4 times 7, right? So 29 mod 7 has to be 1. So we're landing on 1 again. So notice 1 has 1 in it. It's kind of funny how that works out. So we got to check what h prime of 29 is. Well, that's 5 minus 29 mod 5. Which this, well, 29 mod 5, okay, 25 mod 5. That's 0, right? But this is 4 higher than that, because 29 is 4 higher than 25. So we have this being 4. 5 minus 4 is 1. So what does that mean? That means we're going to have a hop size of 1, just like we had with linear probing that one time. So now notice that I have 1, so I'm just going to hop on down one single hop here. And 29 goes right here. Piece of cake, right? So this is how double hashing works. So everything I told you about insertion, removal, searching, it's the same as it was for linear probing, except just this is different. That's it. And the time complexities are the same. The worst case is still big O of n for get, put, and remove. Average case with a good hash function, good as we defined earlier, will be big O of 1. And keep in mind, remember, the load factor in these cases is always going to be at no more than 1. In fact, it stays, if you don't have it getting full, then it has to be the case it's less than 1. So just please keep that in mind. Just remember, even though that is the case, as the table fills, you will have it where you're going to have it where you're going to start, sorry, I'm getting really excited here. You're going to have it where collisions are bound to occur. Like the intuition isn't just enough. It will happen, and it will happen more often as it gets full. So that's why I'm mentioning that the load factor is rather important. So I will come back to that actually just in a moment. So I thought it would be very important I show you why the table size for double hashing, as I said previously, it needs to be a prime number. So again, like I said, I'll have some pseudocode in the notes for what we just discussed here. So let's see. Let's try doing this. Okay, so I want to show you how this can go very badly. So I'm going to address the question of why must M be prime in double hashing. So with our H prime. Sorry, I'm getting really excited. In double hashing. So I'm going to show you a pretty basic example. Now, what I'm saying is that having it where the table size is M guarantees you will not have this situation happen. That's what I'm claiming here for you. I'm not saying that you can find weird cases where, or other cases where it does manage to work without this happening. I'm saying that this, making sure the table size is prime will ensure this will never happen. We're going to have 8 slots this time around. 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7, and table size. There's table T. And we're going to have H of K. It's going to be K mod 8, like we've been doing up to this point. And the secondary hash function. Secondary hash function. This time is going to be 7 minus K mod 7. So as I pick the prime number that is less than 8. So next, let's try putting some things in. I'm going to put 2, 6, and 10. Now this is a very specific example, but I encourage you to think about other ways you can get this to happen. So if I do 2, 6, and 10 as the keys, well, if I do 2 mod 8 is just 2, right? I'm sorry, I'm just getting really excited here. I had to really drink something. Okay, here we go. That's much better. Sorry, I'm getting very excited about this one example. So if we have 2, you know, it goes right there. Piece of cake. 6 should be 6, right? Those are rather straightforward, right? How about 10? Well, 10 mod 8 is, well, it's 2 higher than 8, and 8 mod 8 is 0, right? So this will be 2. So you know you're going to get a collision right here. So we get a collision. So what do we do when we do this? We have to figure out how big the hop size is. So we got a H prime of 10. Well, this would be 7 minus 10 mod 7. Well, 10 is 3 higher than 7 mod 7, right? So that means that this will be a 3. 7 minus 3 is 4. So our hop size is going to be exactly equal to 4. So please keep that in mind. So please keep this in mind. It's very important. So please notice, and I'll start off by just showing you how this works out. But I hope you'll see what's the issue here. So I have a collision right here. So I hop 4 to here. Well, there's something there, right? That's a problem. That means I'm going to continue the probing sequence. So now I go 2 times that. So now I got to make another hop of 4. So 1, 2, 3, 4. Well, there's something still there, right? So 3 times the hop size. 4 times the hop size. 5 times the hop size. 6. 7. And so on, and so on, and so on. Do you see that I'm never, assuming that I don't have anything in check to make sure that I stop doing this eventually, 10 is not going to get inserted in here. So key 10 never gets inserted. So you might ask, what is this about? So what is kind of like the machinery underneath this that's making it so that we can make sure that we explore every one of the table slots eventually? Because in this example, we only get this situation happening. Well, it's all about some number theory. Now, I'm not going to be proving this claim for you, but it's important that the size of the table and h prime of k, whatever h prime of k is, they have to be what we call relatively prime or coprime. So I'll tell you what that means. So what does relatively prime mean, which is sometimes called coprime? If the only positive integer factors or divisors of two numbers is 1. So if I give you two numbers, well, two positive integers, and I ask if they're relatively prime, if I look at their divisors, the only one they're allowed to have in common is 1. So just as an example, 3 and 8 are relatively prime. This is because the divisors of 3 are 1 and 3, because it's a prime number, and the divisors of 8 are 1, 2, 4, and 8. Notice that the only one they have in common is the 1. So picking the hash function the way we did, remember, Q is always less than capital M, and M is a prime number, so you can guarantee that whatever you get as a result of a prime number versus anything that isn't a prime number, but it's never going to be as big as that prime number, is going to be relatively prime. That's the explanation I'm going to give you here for why this works. But I will not prove that this will, so I'm not going to prove this claim, but this will, ensuring that the table size is prime like this with our hash function for the secondary one, this will ensure that we explore the entire table.